All right, so what we want to do today is to kick off in the organic section functional groups. So far all we've done at stage one is we've talked about what an organic molecule is, which contains carbon, and then we introduced you to hydrocarbons, and then we introduced you to alkanes, alkenes and alkynes, and then we've done how do we name structures, okay, using the UPAC or that International System of Nomenclature. And then yesterday we did isomers, didn't we? Yeah, we did isomers yesterday, and we learnt how to actually draw isomers for a whole range of alkanes, alkenes and alkynes. And then we did a little bit on the reactions of alkenes and alkynes. We talked about combustion reactions, which is reaction with oxygen to produce carbon dioxide and water. They're all the same products of combustion. And we said the combustion was exothermic. And then we talked about addition reactions, and we talked about adding bromine across a double or triple bond. We talked about adding hydrogen across a double or triple bond. Okay. We talked about saturated and unsaturated compounds. Now, this is probably where the real, I'll say this is where the real chemistry for organic actually starts. And we're at year 11, we're just at the tip of the iceberg, all right? We're only looking at the surface. So when we look at a functional group, and the functional groups that we're going to look at are going to be alcohol, we start off with. It's a general functional group. Then we're going to look at carboxylic acids, and then we're going to look at esters. So we do 3 functional groups at stage 1. For your information, okay? At stage 2, here we go. So at stage 2, you'll be doing alcohols. At stage 2, you'll be doing aldehydes. You'll be doing carboxylic acids again, okay? Which is what we're doing at stage 1. Then you'll be doing another group, okay, again a repeat of what we're doing this year, of esters. And then you'll be doing a group called amines. And then you're doing a group called amides, okay? We don't do it anymore, all right? But where the X is chlorine or bromine or iodine, they're called alkyl halides. These are all the functional groups that we do at stage 2, okay? Functional means, what do you think functional means in the context of a chemical? It's working, it's the active site, okay? So when we produce molecules, when people make molecules, whether it's a plastic or whether it's a drug, okay, whatever it is, if we can identify the structure, we can identify the functional groups in the structure. That's all those drugs and all the chemicals are that exist. They're a combination of carbon and hydrogen, and one or more of these functional groups in a certain position in the structure, and that's the functional group. So synthetically, we can actually, in theory, all right, make a whole lot of different chemicals if we know what they look like. That's all we need. And technology obviously allows us to look at the structure these days. So we can use a whole lot of different apparatus to tell us, for example, what the chemical is and what it looks like. So if we come up with this magical drug to cure cancer, let's just say it comes from a plant, then provided we can extract that drug from the plant, we can work out its structure. If you can work out its structure in the lab, we can make it, all right? And that's where a lot of chemistry happens. It's in the lab with things called research scientists, or people called research scientists, and they do something called retrosynthetic analysis. What do you think that means? Retrosynthetic analysis. I used to do that many years ago at uni. Retrosynthetic analysis. Any ideas what that means? It just means working backwards. So if I ask you to build a car, for example, you would actually have to take it apart, piece by piece, and there's videos on YouTube on that, by the way, as well. If you pulled the car apart, then you'd work out how to build it from scratch, all right? So it's no different to a molecule. So I'll give you the end product. I'll say, here's the thing I want you to make, all right? Now work out how to make it. So then you go back. You can't do the whole thing in one step, by the way. It's a whole lot of steps. It could be, to make some drugs, there could be hundreds of sequences of reactions that have to be done to get to the end product. It's not normally one or two reactions. That's why the things are so expensive, because you just can't make them in one or two steps. There's lots and lots of steps that have to happen to bring about the structure that you want. Anyway, enough of that. So these are the functional groups we're going to talk about. Not this year, some we will. Okay, so this year we're going to do alcohols, carboxylic acids, and esters. Only 3. I'm going to make it easy for you this year. Okay? Alright, let's look at the alcohols functional group. So the distinguishing characteristic of any alcohol is that it has got an OH in its structure. But not to be confused with an OH that is in a carboxylic acid, because it's not an alcohol anymore. It's not. It's called a carboxylic acid. So what I mean is this. So if I've got a structure like this, and you might say, oh, but wait a minute, that's got an OH in the structure. Yes, it has. All right. But this OH is sitting next to what we call a carbonyl group. This OH is sitting next to a carbon, and on that particular carbon here, I can only have hydrogens or carbons. If it's something else, then it's not an alcohol. Okay, it's a different functional group. So that's something to consider. So we want carbon attached to OH anywhere. In that instance, then we have definitely got, okay, what we would call an alcohol functional group. Also forgot to mention that with all the functional groups that we do, there are commonalities. We do the same sort of thing. The first thing we do is, what's the structure? Here we go. What's the structure? Second thing, how do we name these functional groups? So we haven't actually named alcohols before. The third thing is, how do we make them? So how would I actually produce an alcohol, all right, in a lab environment? What reactions do they undergo? Okay, and the fourth thing, not on the board yet, is how do I test for? Can I test for an alcohol? It's the same, regardless of the functional group. So when we do carboxylic acids, the first thing will be, what do they look like? How do I name them? How do I make a carboxylic acid? What reactions do carboxylic acids undergo? And how do I test for a carboxylic acid? Hopefully you can work out that when we look at how we make a carboxylic acid, obviously to make a carboxylic acid, we have to start from a primary alcohol. When we carry out a process of oxidation, okay, we end up with a carboxylic acid. So if I ask you, how do we make ethanoic acid? Here it is. You would say, I have to actually reflux ethanol in the presence of dichromate, and we'll talk about what reflux is in a minute as well. And then I need to distill off my carboxylic acid at the end of that procedure. Who's done distillation before? We haven't, have we? It's all new. Who knows what reflux is? No, we haven't. It's all new. Okay? So we're going to do these processes. These are very fundamental in any organic, okay, reaction. Reflux distillation. Okay? There's another process I haven't talked about, which is called extraction. All right? And there are various ways to extract a chemical as well. All right? Now, let's get started. So, 3 types of alcohols: primary, secondary, tertiary. And the way that you actually determine that is to look at the carbon that is directly attached to the alcohol. If you think of primary meaning 1, this has got only 1 carbon chain. Okay? 1 carbon chain, primary. Okay? Now, but that also means, by the way, that this alcohol here is also, fairly obviously, that's a primary alcohol as well. That's got no carbon chains. It's only got a single carbon attached to the OH. Secondary, 2 carbon chains. So here they are. R is a carbon and R dash is a different carbon chain. But I could have the same carbon there, it wouldn't matter. Alright? And that could be any carbon, not a hydrogen, it has to be carbon chain. So we'll put that dash back in there. Tertiary means 3. So we look at this carbon again, here it is, and it's got 1, 2, 3. It's got 3 carbons attached to the functional carbon where the OH is bonded to. So we can categorise alcohols as primary, secondary, tertiary by looking at that individual carbon, and it should be pretty straightforward. Next, how do we name them? Well, if we're naming an alcohol, the same process we use over and over again. So the first thing we have to do is we've got to pick out the longest carbon chain, and we'll have to number it from the end with the nearest functional group or the nearest substitution. Well, there's only one functional group here, it's pretty easy. Carbon number 1, carbon number 2, carbon number 3. Here's my functional group, so we identify that as an alcohol. It's a very simple alcohol. So this comes from 1, 2, 3, 3 carbons, propane, because that originally was propane, so propane, and on carbon number 1, we've got an alcohol. So alcohols are named with the ending OL, ol, which comes from the name alcohol. Funny about that, alright? So that's where it comes from. That's where the ol comes from in naming alcohols. It doesn't always carry through with other functional groups, but for alcohols it does. Or, if you wanted to take the alcohol out, we also call an alcohol a hydroxy. Hydroxy, hydrogen, oxygen, okay, OH. This is the preferred method though, okay, is where we're using the ol in the naming of the structure. Alright, any questions so far? Everybody cool with that? Yeah. Alright, it's all new, so if you want to ask questions, now's the time to fire away. Alright, making alcohols. Now, again, like I said, the pattern is the same for all the functional groups. So how do we make alcohol? By the way, the general term alcohol actually means ethanol. That's a common name for ethanol, okay? That's the common name for ethanol. So when we're talking about alcohol, we actually are talking about ethanol. If we're talking about alcohols, the functional group, that's not ethanol, that's anything with an OH in its structure. Alright? So just to distinguish between the two. So if I'm going to make any type of alcohol, alright, and this happens to be ethanol, which is the same as alcohol, I have to start off with a double bond if I'm going to use this method, and I have water. It has to be what we call acid catalyzed. I didn't talk about that before, but it has to be done in the presence of acid, normally concentrated sulfuric acid. Now we actually don't do that reaction. We don't make alcohols like that, okay, in the course. I'm just highlighting it for you that that's how we could make an alcohol. So if I asked you, how would we make this alcohol? If I asked you to do a retro-synthetic analysis on this one, anybody got any ideas how I would make this alcohol, propane 1-ol? What would the precursor for that structure have to be? Given that one. Any ideas? Omar? The one on the what?
At the top of the underdeveloped structures, that structure, that first structure.
Where? Yeah, so if I've got an OH here, Kane, what would the precursor to this look like? Have a go. What would the structure be that I have to start off with to get that?
CH3 and CH3 with a double bond.
Good, double bond, okay. It would look like this. It would be, this structure here would be the precursor to this one. Okay? So it would be 2 H's there, H there, as Kane said, the 3 hydrogens there, and I would have to do this, add water, and I should end up with that structure. But of course those of you who are thinking would say, how do I make it go onto the end carbon or this carbon? It's another question we'll leave for later, alright? Because you can't control that. So, you're going to get some of the compound that's going to have it on carbon number 3 and some on carbon number 2. Okay? Which do you think is, just common sense, which do you think it's going to be the most likely carbon to go on? Is it going to be the end carbon or the first carbon in? Probably the end carbon. Why do you say the end carbon? It's easier. Why is it easier? Yeah, okay, so that's going to be like on the boundary of the structure. So it's probably going to attach to the outside of the structure where that end carbon is. Most likely, alright? But not all the time. because the structure is not linear. Remember, it's going to be tetrahedral. So all the carbons are equally exposed. But we won't go there yet. All right, what do we get up to? Oh, so this is just general structures for making any alcohol. This one here is the main one that we look at, all right? And there is a video in Sector, I think where a guy's making beer. But you can do this yourselves, okay? Doesn't take a chemical wizard to produce alcohol, or ethanol, as we're going to call it. So all you need to have is a solution of sugar, which is what we use. We require an enzyme. Yeast is an enzyme. It's an active enzyme. Okay, it's a living organism, which you can buy anywhere. Okay, there's certain yeast, by the way, for certain functions. So that it's not the same sort of yeast that we use for bread. Not the same sort of yeast you'd use for, say, pizza dough. So it's a little bit different. And it's not the same sort of yeast you would use in the fermentation of beer either. So although we use the general term yeast, there are certain types of yeast that favour fermentation of straight sugar, all right? So all we do is we make up a sugar solution, pretty easy, okay? Most people got sugar in their cupboards. You make up a sugar solution, you add the yeast to the sugar. Normally you have to heat it up a little bit, okay, to get the reaction going, all right? Once you start adding yeast to the sugar very quickly, within a couple of hours, fermentation begins. And you know fermentation's begun because carbon dioxide bubbles come out of the solution. Okay? So when they ferment wine, and some of you might have chosen that in the issue study, when they ferment wine to produce grapes, they've got to crush the juice first, or they extract the juice from the skins. Okay? Then they take the juice, which has got a certain amount of sugar in it, they add the yeast, okay? And all they do then is sit back for a couple of days and enjoy watching the fermentation reaction, all right? That's all it is, and it can be done in open vats, exposed to the atmosphere. So fermentation of wine is the easiest thing to do, all right? However, you need to be careful about the amount of oxygen around. Anybody got any ideas why that is? So if I'm going to ferment sugar to produce ethanol, once I produce the ethanol, that's okay, but I need to keep the ethanol away from the air from that point onward. Any ideas why? Omar?
Doesn't alcohol evaporate?
Yeah, it's got a low boiling point, about 40 something degrees, so yes, we don't want to lose our alcohol. That'd be tragic if you came back and it was all evaporated. For those of you that drink alcohol, which is none of you, but I do, all right? Okay? Yes, it's going to react with oxygen in the air, okay? And your parents may have sort of worked it out, maybe by accident, but if you have an open bottle of wine, for example, and not that you would know this, but if you started to drink it today, and then you leave it open to the atmosphere, and you come back to it tomorrow, people will like say, oh, it's gone off, all right? It actually hasn't gone off, it's oxidised. And it's turned into, what does ethanol turn into when it oxidises? People use the term, it tastes like vinegar. It's ethanoic acid. It is. It actually turns into ethanoic acid, okay, if it's left in the contact with the atmosphere. So this oxidation happens naturally anyway. So if I just leave ethanol in the atmosphere, exposed to oxygen, it really turns into acetic acid. That's how they make things like vinegar, white vinegar, and red vinegar. All they do is they take white wine, bubble oxygen through it, it turns into white vinegar. The red vinegar, or balsamic vinegar, take red wine, bubble oxygen through it, balsamic vinegar. That's pretty easy. Alright, so the process of fermentation is important, okay, because there's huge industries, particularly in South Australia, okay, around producing alcohol. And that's what your issue study is about, the positive and the negatives, okay, of alcohol in our society. Alright, so we're pretty lucky in Adelaide if you drink alcohol because we've got all wineries all around the district, okay, and of course there's lots and lots of breweries in Adelaide. There's Cooper's Brewery, West End Brewery as well. So lots of stuff is made in Adelaide, alright, locally. We used to be able to do an excursion there, but we can't do that anymore, mainly because you're too young, and secondly because it was very difficult to get into these places. But it's pretty simple. They just ferment things on a large scale. All right. So in other words, they ferment 5,000 litres at a time, whereas if I'm doing my own here at home, I'll do 21 litres. It's only a drum this size, okay? Exactly the same process, it's just scaled up on an industrial process. That's all it is, okay? All right, reactions of alcohols we need to go through, all right? And I'm going to have to make some space over here to explain reflux and distillation. All right, if I take a primary alcohol and if I carry out what we call oxidation with dichromate, it's got to be acidified, I end up with an aldehyde structure. Now we're not going to do the aldehyde functional group, but I'll show you how it works in a minute. And if we keep on going, we end up with a carboxylic acid structure. So that's a reaction of all primary alcohols. They all produce an aldehyde, then a carboxylic acid. Now, I want to talk about both reflux and distill, okay? The differences between the two. So if I'm going to do what's called a reflux in an organic reaction, in a synthesis, synthesis means obviously making it. For us, we're pretty lucky. For our purposes, I'll actually put down that we're going to heat it like this. We're going to use round bottom flasks and we use heating mantles. You might see the sort of year 12s. Did you see the year 12s and have them set up in class? Did you see it? Do you remember those things set up? Maybe not, but next week or the week after, we'll be doing a week of organic where we do reflux distillation the same week. We're going to make an ester. All right, so typically what happens is this. Now, I'll do it with a pear-shaped flask, okay, but we'll be using a round bottom flask, okay, and I'll grab the equipment out for you in a minute so you can see how it looks. Now, this is water for the purposes of our experiments, okay, and this is called the round bottom flask, or I should say pear-shaped flask. And this is called a condenser. Now, a condenser, what we're going to do is I'll go and grab this out of the cupboard so you've got some idea about what I'm talking about real time. So just bear with me for a second. I'll try and get a kit. Is there what? Yes, you'll be doing prep report on these, yeah. Okay. Now, here we go. Whoops, I need to get a flask. So what we're going to be doing in our experiment, okay, is we'll be doing it on a round bottom flask with a heating mantle, which is electrical. That'll go around the base. Here is the setup for reflux. Okay, now we don't hold it in the atmosphere like this. It gets pretty hot after a while. It's all clamped, okay, and I'll show you how to do that. But the condenser is a hollow glass tube. Right there, so it doesn't walk away from me. And it's still a little bit wet from when we were using last time. So it's hollow glass tube, okay? On the outside, it's got a water jacket, all right? So the theory is, when I run the water in, this whole outside fills with water, okay? And consequently, it condenses. It turns a gas back into a liquid. Why do we want that? Well, if I'm heating a chemical in here, all right, and this is the process of reflux, that's what it looks like, the whole idea is to keep heating the chemical for a long time, but not to lose any product or any reactant. The heat can escape to the top, heat can get out of there, that's fine, okay, but as the chemical comes up, as it vaporises, because I'm boiling it down the bottom, it'll vaporise, it'll come up the top, it'll hit the cold water and it will go down again. Okay? So then the next chemical boils, whenever that temperature is. It'll vaporise, it will go up, hit the cold water, come down again. The next one boils, goes up, hits the cold water, comes down again. It recondenses. So reflux allows me to boil things for a really long time, okay, at a high temperature without losing anything. So the volume here stays the same all the time. Now if I did this, if I then heated up my reactant and come back about, 2 or 3 minutes later, that's going to be empty because it's gone to the atmosphere. We don't want that to happen, so we simply do this. We put a condenser on the top, okay, and and that allows everything to recycle back into the flask. That's what I mean by reflux. Okay. Yeah, this is, I can't just fill this up once. We hook this up to the tap, okay? Unfortunately, we haven't got constant flow taps, some labs do. And the water just is, and this goes into the sink here. I'll show you how to hook it up later. But this just sits in the sink and it's continuously flow of water, all right? Yeah, just goes from the bottom up. Anybody know why we have to fill it from the bottom up? Bottom up. We fill up the condenser from the lowest point to the highest point. Omar? Yes, sort of, okay. Yeah, cold goes in the bottom, but if I filled it from the top, do you think the whole thing's going to be surrounded by water? It's not. So I'm going to get all the condenser, but it's not going to be cold. There'll be spots that don't have water. Water's going to flow down straight out. So I've actually got to fill it up. This whole thing, for the whole time I'm using it, has to be surrounded by water. It's got to cool things down. That's how it works. Okay, so that's reflux. I'll come back to distillation right now. All right, distillation. Slightly different, okay, and we'll show you what a distillation apparatus looks like as well. So same deal, and my diagrams are not very good, I'll emphasise that. Horrible diagrams. What? I'm recording this, Mr. White, but say hello. Just say hello. It's alright, mister. You can come in. Come in. Join the video. Alright, now, what we have for a distillation setup is a little bit different. So, this is sealed, okay, at the top. Condenser's still there. Here it is. Water goes in through the bottom and out through the top, okay? The chemical that we're distilling is this one, okay? And we can have 2 or 3, 4, doesn't matter what it is. We could have a whole lot of chemicals in there that we want to actually separate based on boiling point. So all we need to do, okay, and it's easier said than done. So what happens is this. So this is a still head. Here it is here. All right. And on top of the still head, there is an actual, it's called an O-ring. Okay. And the O-ring is where the thermometer goes in, and you tighten it, and it holds the thermometer vertical. The thermometer sits about here. All right. Just where the vapour is going to condense. It's an approximate indication of the temperature. All right, this sits on the top of your round bottom flask, is what we're going to have. There's a thermometer here. The condenser is attached. There it is there. Okay, essentially, and if your kit has one, yeah, this one has. It's got a receiver. It's called a receiver adapter, and then the receiver adapter sits on the end. Okay, and what happens is, as it vaporizes, okay, any chemical. I'm just going to take that off so I don't drop it. As it vaporizes, the chemical comes up to here, okay? We record the temperature at the top. It'll come down the condenser, it'll hit the cold water, and it condenses. And that keeps on happening, all right, for every chemical that we've got in here. Okay? So it's just basically separated out on there by their boiling point.
This time they will escape.
This time they will escape, yes. We do want them to come out this time, and that's how we collect them. You'll see that on the board behind me. We typically have a rack of test tubes, okay, or other flasks, it doesn't really matter what. And then as we record the temperature here, we just collect them at different boiling points. That's it. And as we collect them, we move it. We don't move this whole apparatus. All we do is we get our test tube rack, we just move it along, okay, as we collect different chemicals at different boiling points. It's that simple, all right? So that's the process of distillation, and I'm not going to go into distill as formed. I'm not going to worry about that, all right? All we need to understand is that if I'm going to produce a carboxylic acid from an alcohol, I'm going to use the reflux setup, okay? Not with the still head there, of course, that's gone, all right? So we're going to use reflux setup. If I'm going to use a distillation, if I have to actually separate the compound straight off, then we're going to use an actual distillation setup, okay, to separate out. Now, this is all equipment you haven't used before, okay? So don't worry, there's some lovely YouTube videos of me setting it up for Year 12s that you're going to watch before the experiment. So you have plenty of opportunity to have a go at setting up that equipment. All right, 2 more things we have to do for the alcohols. So oxidation, just to finish off the alcohols, because this is the only thing that we need to look at. All right, we did oxidation of primary alcohols. The secondary alcohols, all right? Look at the secondary alcohol. Oh, I forgot some functional groups over there that I'll put in now. A secondary alcohol, let's do one. We'll do this one here. There's a secondary alcohol. Okay, 1, 2, it's got 2 carbons on the chain. If I oxidize a secondary alcohol in the presence of dichromate, I end up with a ketone. So it goes to this compound here. Now that is a functional group that I didn't mention, okay, over here. So a ketone looks like this. There it is, okay. It's just a carbon double bond O with 2 carbon chains, okay, on either side. All right, that's the secondary alcohol. If I do the same thing with the tertiary alcohol, let's try that with the tertiary. So we'll do CH3COH, CH3, CH3. If I do that with tertiary alcohol, and we'll use dichromate again, I end up with no reaction. None at all. I need some orange, and I need some green. Okay. While we're on the alcohol section, this could be not only of these reactions that alcohols undergo, it could be a test for alcohols as well. Because, hopefully you understand or can remember, what colour is dichromate? Orange. It's orange. Okay? So dichromate is orange. So what I would observe here, alright, is the orange dichromate, when it reacts in a redox reaction, eventually goes to green chromium ions. So the colour change, if I get a reaction, is orange to green. So that could be a test for a primary alcohol. But unfortunately, it's going to do the same thing with a secondary alcohol. So it's not going to be a very useful test for a primary and a secondary alcohol, because I'm going to get the same outcome, the same colour change. So this will also go from orange over this side to green, okay, as the ketone is produced. But if I wanted to distinguish between a primary or a secondary alcohol and a tertiary alcohol, it would work. Because it's simple. This, the orange colour, if it's tertiary, at the end, when I carry out the reaction, it's going to remain orange. So that's a definite indicator of the tertiary alcohol, if I know that I'm working with an alcohol. Okay? Because that would be the same outcome with an alkane, or an alkene, or an alkyne. So, we can use the dichromate not just for a reaction, but also a test for. Okay, that's really about all we're going to cover for alcohols. Any questions, Param? Because I told you there's no reaction with tertiary alcohols. Yeah? Got it? You've got to learn it.
What happens with
The dichromate stays in solution. It doesn't do anything. It doesn't react. Okay? So, when you learn, like I said, there are some chemicals that undergo certain reactions and other ones don't. Some salts are soluble, some salts aren't. Okay? How do you know? Because you learned it. Okay? Why don't the salts dissolve? It's obviously something to do with how those ions are bonded in solution. Why doesn't a tertiary alcohol react? Hopefully you can probably work out that in order for this to react, it has to get to this carbon. Yeah? This carbon is now not visible. It's surrounded by 3 other carbons. So therefore, that's why a tertiary alcohol does not react. This alcohol, yes, I can get to that one. And this alcohol, yes, I can get to that one. So I can't make a tertiary alcohol undergo oxidation with dichromate. And it's just a fact you've got to learn. Yep.
What's the thing that attaches to the carbon? Yeah. Is it the OH?
What are you talking about?
What attaches with the carbon?
What attaches with the carbon?
Yeah.
Well, down here, you can see the first one is an aldehyde group. Okay? And then over here, it turns into a carboxylic acid. Okay?
What do you call the distillation? What's the process between the...
Alright, what did I call this thing here?
Yeah.
That's called a still head. We'll talk about how to name all these pieces later, okay, when we do the experiment, because you have to take a photo of it, alright? So we talk about a still head, you know, a thermometer holder, a 100 ml round bottom flask, a heating mantle, there's a lab jack, there's a receiver adapter, Liebig condenser, okay, it's not just a general condenser, it's a Liebig condenser, because this is a certain type of condenser. I can get condensers that are like this big, okay, as well, bigger than that, alright, depending on what I'm working with, alright. So there is all different names for the glass apparatus, okay, and I forgot to mention it's all very expensive. So we've got to treat this with some care. Samuel. Okay, here we go. Sam asked a very good question. Why would I need to have a longer condenser, like a larger condenser? Any ideas? Abdul? Could be, if I've got a really large volume, okay, obviously this is worked out for a small volume, this condenser will only work up to about 100 mils. Right, that's one reasonable answer. Omar?
Would the longer condenser differentiate the chemicals better?
It does, okay. So, although we don't use them, okay, the more volatile a chemical, as in if it's got a really low boiling point, it'll go a long way to the top before it recondenses. So if I've got a chemical that's got a really low boiling point, it's possible, in this setup here, I could lose it through the top. Okay? Because that's going to go the greatest up before it recondenses back down again. Okay? So the long condenser allows me to trap all the volatile chemicals. All volatile meaning low boiling point. Now we're stuck with this. This is our apparatus, this is what we have to use, all right? For everything we do, it works fine. But for other chemicals, all right, you may find that you need to change the condenser. Okay? That's the only criteria you have to worry about. Any other questions? All right, that's a long video. We're going to just leave it. That's all the alcohols that we have to do, okay? A little bit of revision there as well.